Oh, okay. All right. Audio's good. I apologize, guys. I kind of should redo what I just. I have to restate say everything I just said. Okay. So again, welcome to today's stream of CosmoQuest Astro 101. I'm your host, Dr. Matthew Richardson, and unfortunately, Joe will not be with us for today's stream. He just recently started a course, and the time at which the course takes place is 1 o'clock p.m. So he's unable to make it for today's stream. This might be true for the future streams, but I can't say for certain just quite yet because we might end up moving the time for this stream to accommodate for his course, or we may keep it at the same time, and then Joe wouldn't be available for the stream, so which would kind of suck. But we'll see. We'll see how it works out. All right. So I was, again, like I do with all my streams, I'm always scrambling to try to determine exactly what I want to talk about. And so I decided I'm going to talk about something that I did for my graduate studies, which was my work on ultra energy cosmic rays. And I don't want to throw anybody in on the deep end of the pool of that topic, so we're going to start off easy today. And we're going to talk about this little thing called the Heelys Criterion. And so to kind of give you a sense of where we're going to be in a cosmic rays journey from its source to us. Let's start off with this background image I'm showing here. So, as we can kind of see, we have this on the far left-hand side of the image of our title screen here. We have essentially a source of cosmic rays, which could be a galaxy, which is being depicted here in our image. We have a galaxy. Coming from that galaxy, we have essentially three different things: a photon, a neutrino, and a cosmic ray, ultra energy cosmic ray. Of course, it can be assumed all coming from the same source. Travels from the source and eventually arrives at us, where, as we see with the photon and the ultra energy cosmic ray, we kind of see like the showers going on there. And of course, the neutrino, which doesn't really interact with matter that much, kind of just passes right through Earth to some extent. But our story kind of begins, of course, at the source, and that is kind of where the Heelys Criterion is kind of associated with. It's associated with source conditions, and so we're going to kind of be talking about this particular theory and its importance in trying to determine the sources for ultra energy cosmic rays. So a quick welcome to everyone. Hello, Uncle Bill Druin. Hello, Guido. Hello, Guido. Excuse me. Hello, Larry. Yes, the Heelys Criterion is what we're discussing today. All right. So whenever you're talking about these sources, there's a few key things, of course, that are going to be required of the source itself. First things first, the geometry. You want to be able to make sure that the physical size of the source can contain the cosmic ray while it's accelerating it. So the geometry of the source is important. Another thing that's also important is the physical power associated with the source. And this is more so associated with how much energy can the source itself depart or give to its cosmic ray, while of course still remaining a source. Well, of course, while still like not basically how much power can the source itself give to the cosmic rays. The next thing, which is important, of course, is going to be radiation losses. While the cosmic rays are being accelerated, for the simple fact that cosmic rays are generally charged particles, and while undergoing acceleration, charged particles emit electromagnetic radiation, they will lose that energy in the form of photons. And so you also have to consider radiation losses while being accelerated close by the source itself. Of course, interactions with other particles, those interactions can cause the cosmic ray to lose energy. You also need for the source to be able to produce the particle fluxes that we observe here at Earth. And lastly, And this kind of ties into the initial image that we saw on the title screen, accompanying radiation. So you'd expect, of course, while these particles are being accelerated, that there will be the production of photons as well as production of, in this case, neutrinos that are associated with the acceleration of the cosmic rays. But for our discussion today, we're primarily going to focus in on the very first 2 points that I make here, the geometry and the source power, because these are the two main things that are generally tied into the Heelys Criterion. And to do so, we're going to have to go through a little bit of math. It's nothing too difficult or anything. It's actually pretty straightforward. But we're going to have to go through a little bit of math, and I've kind of written up something here, and so I'm going to go ahead and bring it up. And so really quickly, I want to make sure that I'm not losing any of the comments here. All right, so the idea we should kind of get here is that we're observing these really high energy particles here at Earth, and for some of the particles, they're exhibiting energies that are on the order of 10 to the 20 eV. And so a while ago, I did a really quick calculation, and if you were to take a cosmic ray that has an energy of 10 to the 20 eV and assign that energy to, let's say, a baseball being thrown, well, that would equate to a baseball having a speed of 54 kilometers per hour or 33 miles per hour for us who live in the US and don't really work in units outside of miles per hour. So for me, it's 33 miles per hour. For you guys, or for anyone who understands kilometers per hour, it would be 54 kilometers per hour, which, as far as I'm concerned, is pretty quick. And so at these energies, the cosmic rays, of course, their physical energies are comparable to macroscopic objects. And so when you think about this, you kind of course, one thing that comes to mind is, well, what sort of sources are being able to produce these particles with these high energies, and by what means do they accelerate the particles up to these energies? And so the Heelys Criterion is really tied into the physical conditions of the source itself. More specifically, its physical size, which for our calculation, the physical size of the source, which we're going to assume is spherical, has a radius defined by the variable r sub s. And the other key thing that's going to be important in our calculation is the magnetic field that's associated with the source itself. And so the idea that I really want us to get set up, I really want us to kind of have in our mind is we have some source, and it produces we have some spherical source of some size with a radius r sub s, and it produces a magnetic field. For all essential purposes for our problem that the equation I'm going to talk about right now, we're going to assume that the magnetic field is uniform. So it's not like it's random. It's not randomly oriented, but it's all uniform in orientation. And we're going to imagine, of course, that we have some charged particle that's kind of trapped in this magnetic field moving at some velocity. Now, with that information, you can go ahead and set up some very simple equations to solve for what the energy of that particle could be. And so to do so, we start off with the fact that, well, if the particle is moving in a circular trajectory, it will have some sort of a centripetal acceleration associated with it. And the fact that it's moving in this circular trajectory is more than likely going to be caused by the fact that it's trapped in some uniform magnetic field. Knowing that information, we can establish that the centripetal force on the particle, F sub c, would be equal to the force that's being put onto the particle due to the external magnetic field. And so using that information, you can even look this up on Wikipedia for centripetal force and for the magnetic force on a charged particle, and you'll see that the equation comes up to be something that looks like this. The mass of the particle times the velocity, its linear velocity squared, divided by the radius of the orbit that it's currently undergoing. It's going to be equal to the charge of the particle. Now you may see this generally just as q, but in this case, I put z times q to kind of give an understanding that typically whenever you're talking about cosmic rays, you're talking about some sort of ion, whether it be a hydrogen nucleus, helium nucleus, all the way up to iron, up to an iron nucleus. The best way to indicate its charge, of course, is by what I'm showing here, c times z. So where I have a subscript particle. So the q, of course, in this case is going to represent the charge of, or the magnitude of the charge of an electron, which also happens to be the same amount of charge that a proton has. And then you simply multiply it times z, which is the atomic number of whatever nucleus you may be talking about that corresponds to the cosmic ray that you're working with. And that would give you the total charge of that particular ion. You multiply it then times the speed of the particle, then multiply that times b and subscript perpendicular. And basically the b with the little subscript what looks like an upside down T basically corresponds to the fact that the component of your magnetic field that's important for this calculation is the perpendicular component relative to the direction of the direction in which the particle is traveling in. And so with this equation, and I've basically kind of explained what the information is underneath the this equation that we're looking at here, what those variables mean. But with this equation, you now have all the information that you need, for the most part, to go ahead and establish what the Heelys Criterion is. As I scroll down, of course, we can make a relationship between the mass of the particle and the particle's physical energy. And basically, we do this by using Einstein's equation, E equals mc squared. Where I must note, though, in this case, that the energy that we're referring to here is the total energy of the particle, and not just simply its kinetic energy. And so, what we now get is instead of an equation in terms of the mass of the particle, we get an equation that relates the particle's energy, its physical energy, to some of the key properties of the source itself. Namely R sub g. Well, let me not say that actually. R sub g is actually just going to be the orbit in which our particle is taking. Really, the only property right now that's related to the source itself is the magnetic field that's being generated by the source. We'll get to physical size in a minute. And so you'd want to take the equation as we see it here in terms of the energy, and you'd want to solve for the orbit in which the particle is undergoing, given its energy and the magnetic field that it's in, as well as its charge. And so we come to this equation where we're basically now going to get that the orbit that the particle is undergoing is equal to the energy of the particle divided by the speed of light times the particle's charge, c times q, and then that quantity being multiplied by the magnetic field of the particles within. Now the key thing is this, though: the orbit, or the circular orbit that the particles caught up in, it must be smaller than the radius of our source itself, which is why we get this condition that basically R sub g is less than R sub s. And so with all of this information, we've kind of established, well, this equation itself is the Heelys Criterion. Basically stating that, one, with R sub g being less than R sub s, the particle's acceleration is being fully contained within the radius of our source, and that two, that the acceleration of the particle is due to the fact that it's caught up in a magnetic field that's being produced by the source. Now, another key thing that you get from this equation, from the Heelys Criterion, is the maximum energy that the particle is able to achieve. And I'm going to quickly stop for a second and look at the comments. And so how common is a 10 to the 20 eV cosmic ray? And that is a very good question, actually. So if I'm remembering correctly, once you get somewhere close to these energies, we're talking about a single particle per square kilometer per century. So these particles aren't common at all. They're very, very rare. And typically, in order for you to be able to observe these particles, I'm kind of actually going outside of the topic that I wanted to stick to today, but your question is a good question. Typically, to observe these type of particles, you need to have, assuming you're trying to detect, how can I put this? So to understand this, you need to understand that we don't directly detect these particles. What happens is the particle comes in from outer space, interacts with the particle in our atmosphere, and produces a shower of particles. And from those shower of particles, we also get the emission of light. And so if you're trying to detect the particle, that is the original cosmic ray, by means of the secondary particles it produces in the shower, you need to have extremely large detectors, or not extremely large detectors, but you need to have a lot of detectors that cover a very wide surface area on the ground. So yeah, by a bucket load, right? So muons. So the muons are going to be produced. So typically, what happens is you get these secondary particles, and amongst these secondary particles, you're producing pions, charged pions. Now, eventually, the charged pions, though, they end up decaying into the muons once they reach a critical energy. And so it's typically the muons that you're detecting with your particle detectors. But to detect, of course, all those muons, you need an array of detectors that cover a really large area. But yeah, to get back to this though, so the possible sources. So with this equation, of course, you can establish, of course, what type of sources that you'd need to get, or that you'd need to produce particles of specific energies. But another key thing, though, is that you can change the subscript on the energy, right? Given these conditions, right? Assuming that the particle is requires to use the entire radius of our spherical source, and of course the magnetic field for the source is probably going to be set to a specific value. You can get something else. When you set R sub G equals R sub S, you get the following. You get the maximum amount of energy that can be given into your cosmic ray. And so, this is all theoretical. And the reason being is because whenever you're considering a source for cosmic rays, there aren't any sources that across the entire region of the source, its magnetic field, assuming that it has one, and it's a significant magnetic field, that the field itself is going to be uniform. It's typical that, of course, that probably on very small scales it'll be uniform, but on across the entire region of the source itself, it's not going to be uniform. But you can be able to determine what the maximum. You can kind of sort of get a sense of what the maximum energy can be departed into the cosmic ray itself. Now, we haven't really discussed the mechanism, of course, that can achieve the particle accelerations that would be needed to kind of get to the energies that we see here at Earth for cosmic rays. But this is a very good starting point, of course, for being able to determine the type of sources. And so kind of using the equation that we see here, E max is equal to the speed of light times essentially the charge of the particle times the magnetic field of the source itself times the radius of the source, we can establish a plot. And this plot is what you probably typically see online if you typed in Heelys Criterion. So let me quickly bring that up. Okay, that didn't work. Let me do that again. So we're going back here, and we get this plot. And so basically, what we're seeing in this plot is along the y-axis is magnetic field, and along the x-axis is, or more specifically, along the y-axis we have the magnetic field of the source, and we're plotting it against the physical size of the source along the x-axis. And from all the research that has been done on the various astronomical sources in our universe, we can kind of see what type of sources can produce cosmic rays of what we're seeing here, 3 different energies. The bottom solid line corresponds to a cosmic ray with the energy that's somewhere in the neighborhood of 100 eeV, which is another way of saying 100 times 10 to the 18 eV. And then we move up to cosmic rays of, and one thing they do note here is also the type of cosmic ray we're talking about. So that bottom line is actually for an iron cosmic ray, an iron nuclei cosmic ray that has an energy of 100 eeV. The 2 top lines we see above that, the dotted dash line and the solid line above at the very top, correspond to protons, proton cosmic rays of energy from 100 times 10 to the 18 eV, which is the dotted dash line, or the dotted line, to a proton with an energy of 10 to the, I think that's 21 eV. And so basically that's what the Heelys Criterion allows us to do. It allows us to establish essentially what type of cosmic rays can be produced by the source itself. And if you kind of look at the far left at the top, you kind of see a neutron star far up there, basically meaning that this little circle that we're seeing associated with neutron stars, that circle corresponds to the area of parameter space. In this case, the parameter space being magnetic field versus size of the source. That parameter space is what we'd associate with neutron stars. And these neutron stars can generate, we see that these neutron stars would be able to generate cosmic rays or proton cosmic rays at these energies. And so that's basically how you should be looking at this curve. Now, you get different lines, of course, and it will be highly dependent upon the type of cosmic ray you're referring to. Or more specifically, what I mean by that is whether it's an iron cosmic ray, a magnesium cosmic ray, a carbon cosmic ray, and so forth. Oh, I'm sorry, is it small? I apologize. So yeah, the x-axis is not distance, it's physical size of the source. That's right. I am so sorry. Let me see if I can make it bigger. Where is that? I think I should be okay if I zoom in like this. Let's see if it's a tad bit bigger. Okay, maybe I can't make it bigger. All right. Let's bring that back down, actually. So yeah, I apologize for that. I wish I could make that a little bit bigger. But yeah, the x-axis is the physical size of the source itself, and not distance to the source. Now, of course, this only establishes what sources, given their physical size and the magnetic field that's been determined to be associated with that source. It doesn't actually clear, though, the other remaining conditions. So the Heelys Criterion only states, only gives enough information about the geometry and the source power. It doesn't really talk. It has nothing to do with, of course, the radiation losses that the cosmic ray will experience while being accelerated, nor the interactions between the cosmic ray itself and other particles while being accelerated. Now, we will be coming back to these topics in some of the later streams. But for right now, I kind of figured that this would be a nice, easy way of introducing the topic. And the math itself isn't that bad. As we begin to move on, though, of course the math will get a little bit more difficult, and I will try my best to make it as simple as possible. Because I want you guys to love this topic as much as me. So, but for the most part, that's pretty much my my presentation for today. Um, there will be a lot more to come on this topic, and I might not actually cover it like in like sequentially. I might, from time to time when I can't think of anything else to talk about in astronomy, even though there's so much to talk about. I mean, I might end up just coming to I might end up coming back to talking about cosmic rays. So whenever I say curve, yeah, sorry about that. So actually this would be considered a curve, right? Whenever you're talking even about a line, with plots, whenever someone says curve, they just mean they could be talking about, as you see in this case, a line or something that doesn't look like a line. But in reality, this line does have curvature. Thank you for showing up, Guido. And I'm so sorry you weren't. Hopefully it wasn't my fault that you weren't able to follow. If I said something that's confusing, let me know, and I will try my best to correct it. Note though that these axes are in log space. So if you had them in regular space or unlog space, these would not be straight lines. They would be curves. They'd have curvature to them. But yeah, whenever I'm talking about a plot and I say a curve, the curve itself could be a line, or it could be it could be defined by some other function. Can I recommend a calculus primer? Oh man, it's let's see. I don't know. I'm trying to see if I have my math book nearby. Actually, I do. So, I think I do. Actually, I don't. I have my physics book by me. I don't have my math book. It's somewhere around here. But I have a calculus math book that I used for during undergrad. But I'm pretty sure, like online YouTube, there are people who talk about the different types of equations associated with calculus or theorems but I'll do this though. Whenever I explain something and it requires calculus, I will be sure to bring in a good explanation of the calculus behind it, or at the very least try. Thank you so much, Susie. Exactly. There's lots of videos. Those videos are very helpful. When I was in undergrad, though, and yeah, we didn't have videos to work with. We had a lot of study groups, but yeah, whenever I bring math to anything we do, I'll make sure that if it's something like having to do like a derivative or an integral, I'll be sure now from here on out to make sure I bring an explanation as to how the integral works or how the derivative works. But yeah, guys, that's it for today. That's right, Susie. Yeah, your daughter just recently went to college, right? And she's doing good. That's good to know, actually. I'm happy to hear that. But yeah, just thinking about the math, calculus wasn't that bad. Calculus 2 wasn't that bad. Calculus 3 was challenging. I'll just put it at that. Oh, right. Engineering. Yes. In all honesty, there was an option between two different disciplines that I wanted to major in, and I just happened to choose physics. The other one would have been engineering. Well, Guido, bookkeeping is probably the most important math that anyone has to do. And as much math as I know, I'm not that good with keeping up with with the business side of things with money and stuff. That's all my wife. So see, and it's a difficult choice. It's a very difficult choice to choose between physics and engineering. It just depends on what you love to do. In my case, my undergraduate institution did not have an engineering degree, so physics was the only choice. Okay, well, what I'll do, Larry, is for during my next stream, I'll just quickly, or better yet, I probably could just send it to you through Twitch. Not Twitch, but through Slack. Um, some good recommendations for some books. So I'll look through them and make sure like the information that's being presented is easy to digest. So. Well, Susie, the only thing I can recommend is that just tell her to go with what she loves more. But yeah, engineering is fun. Engineering is being able to like actually apply the math that you're learning with your own hands. It's pretty fun. What I do now is I apply the physics I've learned to like working on my car. So, and I do this because my car is like right that way outside in the garage. So. No worries there, Larry. Some people learn better, like with books, just being able to read. Me personally, if you give me a video, well, if I have the option between looking at a video on a topic and reading a book, I would probably choose the video, like always. I just, I don't know. The same information could be, given by both. It's just that I'm more of a I'm better with like looking at someone else do it. All right, guys. The time is now 12:50 p.m. and I am pretty sure that Daily Space will be airing very soon. So, with that said, I'm going to go ahead and I'm going to log off, and I will see you guys next week with another topic, or probably we'll continue our conversation on ultra high energy cosmic rays. Okay, I'm starting to see you guys love books. I mean, I like I said, I have a lot of books. I mean, I'm looking at my bookshelf right now, and it's like full of physics and astronomy and math books over there. Um, but that was probably the hardest part of learning learning physics and astronomy was actually having to read. Um, I can read just fine. It's just that I mean I don't have much of a love for it. If I can look at a video, I'm so happy to look at the video. But yeah, guys, thank you for watching. As Guido states, 10 minutes more, or about 8 minutes now. Daily Space will be up, and yeah, I'll see you guys next week. Thanks, Adam. All right, guys. Bye.